Next, we have a piezoelectric actuator used to control the aperture of a camera. It has the following transfer function. Draw the Bode plot, calculate the phase in 10 radians per second, and compare the results with the Bode plot. Now, this is a kind of a weird transfer function for a piezoelectric actuator. It wouldn't look like that at all, but let's assume that it is. Right? Just for the sake of our examples here, let's assume that this is actually what is happening. So what do we have here? We have a gain of 10. We have a complex 0 in the numerator. How do I know that that's complex? Because if you calculate the damping ratio, we'll clearly see that this is less than 1. And then you have two poles at the origin and 1 pole at 100. Now, that looks complicated. We have a lot of different elements here. Draw the Bode plots, calculate the phase and magnitude. What do we do first? How do we do first? First, same thing again. We need to prepare the transfer function in the format needed for Bode plot. That entails that the 0, for example, is to be written in this form, and all other poles and zeros as S divided by the cutoff frequency plus 1. So to do that, we can divide the top of the equation by just factor out 100. And then you have S to the power divided by 10 all squared plus 0.5 divided by S by 10 times S divided by 10 plus 1. And you see here the little trick I'm using in just 10 times 10, because then we have S divided by omega 0, which is clearly 10 radians per second. And in the denominator, we'll do the same. Let me find my notes here. And we'll factor out 100. We have S squared times 100 times 1 over, S divided by 100 plus 1. 100 will cancel. And we are left with G of S equals to 10 times S over 10 squared plus 0.05 times S over 10 plus 1 divided by S squared S over 100 plus 1. Okay, so now we have the exact format we want. We have everything is factored out. We have omega 0 for the pole and 0. Omega 0 for the 0 is 10 radians per second. And for the pole is 100 radians per second. And you also have 2 zeta. What is 2 zeta here for the 0? 2 zeta equals to equals to 0.05, right? 2 zeta equals to 0.05. Why do we need to know that? Because that will indicate the magnitude of the Bode plot when we reach the cutoff frequency of the complex 0. Are we good? Yeah? Okay. So now that we have the equation in the standard form, and again, if this is not clear, just ask me to repeat this. If I don't hear anything, I'll keep going. People are very quiet today. And again, the objective of today's lecture is to clear up any confusion in this process. Okay, so now we are dealing with 2 poles at the origin, again, a complex 0 and a real pole. First question is, if you go to the low frequencies, where does the Bode plot start? Well, this is a bit more complicated than the previous example because now we are left with 2 zeros, 2 poles at the origin. So we can't simply take 20 log of 10 and write a flat line at 20 dB. Because now the 2 poles that you have at the origin are adding a slope of negative 40 dB per decade throughout the entire Bode plot. So we don't have that flat line in the beginning anymore. We do have a gain that of 10, and if you calculate 20 log of 10, that is 20 dB. And this is a constant shift to the entire Bode plot upwards. So we have an indication that now the Bode plot is shifted upwards by 20 dB. And we have 2 zeros at the 2 poles at the origin that is creating this slope of negative 40 dB throughout the Bode plot. Why negative 40? Negative 24 each pole. So let's assume that we only had 1 over s, for example, to start. 1 over s squared. We are to the left of all zeros and poles. The only thing left there is 1 over s squared. And of course, the gain. We'll deal with the gain later. So if you only had 1 over s squared, how would the Bode plot look like? Well, it would look like something that passes by 0 dB at 1 radians per second. We saw that in lecture 21. And would create a constant slope of negative 40 dB. So it would have to look like something like this. That would be for 1 over s squared. But we have a constant gain of 20 dB. So if you multiply this by 10, we shift the Bode plot up by 20 dB. And what we actually have is something that starts at 60 and goes down like that, at a slope of negative 40 dB per decade. That's the actual start of the Bode plot. And this slope remains up to the first cutoff frequency, which is 10 radians per second. So we'll keep going down. If here is negative 40, negative 20, 1 decade from now is negative 20. So should be around there. Now, does this make sense? Do you understand why it starts at a 60 dB? Yeah. If you do a decade before, you add 40, right? Because you are going down. Yeah. Yeah. So exactly, that's how we did. We started at 0, then we added 40 to go back in frequency by 1 decade. That would be plus 40, but then we also had to add plus 20 because of the gain. That's why we started at 60 and not 40. Okay. Are we good here? Do we understand why this starts at 60?
Professor, do you mind explaining that again?
Yeah. Let's do that again. Okay. So before any frequency, any cutoff frequencies of the pole and 0, so before we reach 10 or 100, the only thing we are left with is 10 over s squared. Right? And this one, we cannot disregard this in any portion of the graph because it is adding a constant gain of plus 20 dB per decade, plus 20 dB, and adding a slope of negative 40 dB per decade because of these 2 poles at the origin. Right? In this, will act throughout the Bode plot. So let's start by considering only the 0, the pole at the origin, 1 over s squared. If you had 1 over s squared, that would result in a constant slope of negative 40 dB that will pass by 0 decibels at 1 radians per second. All right, so we have 1 over j omega. The magnitude is 20 log of 1 over omega. When omega is 1, this is 20 log of 1 is 0. So the Bode plot would have to pass by 0 decibels at 1 radians per second. And because the slope is negative 40 dB per decade, If we decrease the frequency by a factor of 10, we have to go up by 40. So we would be at plus 40 decibels. One decade from then. In the same way that if you go one decade ahead, it would be at a minus 40. So this is where the Bode plot would start if we only had 1 over s squared. Problem is we don't have 1 over s squared. We have 10 times that. We have 10 over s squared. When you multiply something by 10, we are adding 20 log of 10 to it, which is plus 20 dB. So multiplying something by 10 means shifting everything up by 20. So now the whole curve goes up by 20 decibels, and this is the new start of the Bode plot. Right? So that's where we should see it. Does that make more sense? Yeah? Okay. All right. So that's where it starts at 60, and then we have a constant slope of negative 40 dB because of the two poles at the origin. And we are going down up to the next cutoff frequency, which is 10. 10 is the first cutoff frequency that comes from a 0, that comes from a complex 0. And now the complex 0 will have that a bump that we see with complex poles and zeros. And it's exactly at the cutoff frequency. Remember, from the complex pole, the magnitude at the cutoff frequency was negative 20 log of 2 zeta. This is for the pole, complex pole. And for the complex 0, this would be simply plus 20 log of 2 zeta. This is from the last lecture. We didn't see the 0, we only saw the pole, but the 0 is exactly the pole with a negative sign. So at the cutoff frequency, we shall see a change in magnitude of plus 20 log of 2 zeta. At omega equals to 10, we should have to see plus 20 log of 2 zeta. And we have plus 20 log of 2 zeta is 0.05. I remember from our standard formulation here, what multiplies s over the cutoff frequency is 2 zeta, not zeta. It's just 2 zeta. So that's 0.05, which is about, how much is that? Negative 26 dB. So at the cutoff frequency, because of that a complex 0, it will go down by negative 26 dB. If this was a pole, it would go up. We would see the bump going up. Because it's a complex 0, now it goes down. Here we are at negative 20. So if we add negative 26 to it, we should go to negative 46. So the complex 0 will make this go down by, this is a terrible approximation here, but it should have a smooth curve that it goes down there, because we would be at negative 20 if it wasn't for the complex 0. So you're going down here by negative 26. Negative 20 minus 26 is negative 46. And then we go back. Once we reach that, we go back to where we started. And that's 0. Sorry, that's negative 20, what I'm saying. We just have the bump going down by negative 26. And back to where we started at negative 20. What happens next? Now the slope that was negative 40 dB per decade becomes, because they have a complex 0, the slope is any guesses? What's the slope now past the 0 cutoff frequency? Is 0 decibels per decade, right? The 0 at the complex 0 adds negative adds positive 40 decibels per decade, which means that now the slope that was negative 40 will become 0, and we are going back to negative 20. So we should see a flat line like that, 0 decibels per decade. And that is the case up to the next cutoff frequency, which is the cutoff frequency of a pole. And that cutoff frequency is 100. And add that a cutoff frequency of the pole, we add negative 20 decibels per decade to the slope of 0. So we start to go down by negative 20, which means that at 10 to the power of 3, we should be at negative 40. We are at negative 20. Minus 20 decibels per decade. 1 decade from now, we go to negative 40. And that's it. That's the Bode plot. Yep. So, sorry, should you say that again? A 10. Well, we would be a negative 20, right? If we only, let's say we only had 2 zeros there, right? We would go to negative 20. But so this line would continue there, right? But the problem is we have a complex 0. So that's where the discrepancy comes from. This bump down here comes from 20 log of 2 zeta, and then we go back to negative 20. That's our reference point. Does that answer your question? Yes, if it was a pole, then it would be negative 20 log of zeta, and in which case it would go up. It would peak at right. So a pole at the cutoff frequency when omega equals to omega 0. For a complex pole, we have plus 20 log, sorry, negative 20 log of 2 zeta. And for a 0, we have plus 20 log of 2 zeta. So if it was indeed a pole, because 2 zeta is smaller than 1, this results in a positive number and it would peak, it would go up. But because it's a 0, then 20 log of something smaller than 1 goes down. Yeah. Yes. So this question is, for those who didn't hear, is why is the 0 dB per decade after 10? So we are going down at negative 40 because the 2 poles at the origin. When you crossed the complex 0, the 0 adds plus 40. So it makes it 0. Right? In the same way that the pole would have added, if it was a complex pole, negative 40. And then the slope would have been negative 80. Right? The complex 0 adds plus 40. Okay. Are we good? Yeah. Okay. All good. You understand what is happening with at the 0 there? Should we recap what is going on there, or is it fine? So for the pole, let's just write here. So pole, complex pole, and then here we have a 0. So for complex pole, we have a slope of negative 40 dB per decade. We have a phase of minus 180. And at the cutoff frequency, we have negative 20 log of 2 zeta. If you look at the 0, we have now plus 40 dB per decade. We have plus 180, and you have plus 20 log of 2 zeta. All right, so if 2 zeta is smaller than 1, then this is positive, it peaks. In the case of the 0, it goes down. Let's look at the phase. Where does the phase start? Phase starts at, we have 2 poles at the origin. The phase starts at negative 180. Phase starts at negative 180 because of the 2 poles at the origin. And we will stay at negative 180 up to the first cutoff frequency, which is this 0. This 0 adds plus 180, the phase goes to 0. And then we keep going at 0 up to the next cutoff frequency, which is the pole at 100 that adds negative 90. And that's what we should get. Now we can interpolate this. Because the damping ratio is very small, this should be a very sharp change around the 0, something like that. Okay. Now let's see if our estimate is accurate. We said that at 10 radians per second, we should be somewhere around negative 46. Let's calculate it and see if our estimate here is correct. Any questions about the phase? No? Any questions about the magnitude? No? All right. So let's calculate the phase at the magnitude at that critical point here. If you replace S with the j omega, we have negative omega squared plus 100 plus 0.5 j omega divided by negative omega squared j omega plus 100. And the magnitude is 10 times the square root of real part squared, 100 minus omega squared plus the imaginary part squared divided by the magnitude of omega squared is negative omega squared is simply omega squared. And the rest is omega squared plus 100. At 10, when frequency is 10 radians per second, the magnitude of j omega is approximately 0.005. 20 log of 0.005 is negative 46 dB.